So to answer that question, we will have to try to find an answer to another question, which is what would be the difference in the practical physical scenario where you choose to apply impulse momentum theorem and conservation of momentum theorem. So what situations will you choose either of these is the question. What do you think about it? So we know that momentum is the quantity of motion which is described by mass, the product of mass and velocity. Mu, initial velocity, mass, initial momentum, final velocity, mass, final momentum. Now, how is Newton's law and momentum related? From Newton's second law of motion, rate of change of momentum is equal to the external force acting on it. So if F external is equal to 0, then the rate of change of momentum dp, rate of change of momentum dp by dt is equal to 0. Now when the derivative of one, okay, which this actually means that rate of a constant is equal to 0 and rate of change of momentum is equal to 0 simply implies that momentum should be equal to a constant. Now, when momentum is constant, we have final momentum should be equal to initial momentum, right? And therefore, m into v should be equal to m into u. See, you might feel a bit confused for this part of the solution here. Why? Because we're not trying to learn what is impulse momentum theorem or what is conservation of momentum theorem. We are rather trying to understand in which scenarios are we going to choose them when we get a problem in JEE mains, or for that matter, any of the exams. Okay, so that's definitely going to be a bit challenging. So this part of the solution will not help you to solve the question. We're just trying to learn what to do, which theorem to pick and which to avoid. Okay. So if F external is equal to 0, momentum is conserved. If F external is not equal to 0, momentum changes. This is where the whole discussion is primarily based on if F external is not equal to 0. So law of conservation of momentum says that in an isolated system with no external force, see, these two words are really important. They are in fact very crucial. Isolated and no external. The total momentum before an interaction is equal to the total momentum after this. So if we have a system here, one with the two masses 1 and 2 with the corresponding velocities u1 and u2, initial velocities of course, and the final velocities v1 and v2, then the initial momentum should be equal to the final momentum if this system is isolated and the net external force acting is 0. Okay. Now, imagine you are catching a fast cricket ball as given in the problem here. The ball has some momentum. When you catch it, you bring it to rest, which means this velocity is eventually triggered to 0. So the momentum goes from initial velocity, according to the question, m20 to m times 0. To stop it, your hand must apply a backward force for a short time. The ball will apply an equal and an opposite force on your hand. Why? Newton's third law. Impulse will tell us how much is the total effect the force had over time. Okay. So we have to understand the resolution between these three terms: impulse, instantaneous force, and average force. So the total momentum change due to a force is equal to the force times the very small interval of time. Instantaneous force is the rate of change of momentum for that specific moment. Average force, F average is delta P by delta T, overall effect of the force over a time interval. Overall effect. What would be overall effect? We'll come, we'll come to those minor details later in the section. Okay. Yes. Now I think now we are going through a loop of convolution. Right. It's getting even more complex as we go. Yes, it will, because each and every description that has been noted here is meant for a specific purpose. It means that we are trying to convey some things which will help you solve questions later. Okay. Now, so this was about impulse momentum theorem. Okay. Now let's try to understand what is momentum conserved and the conditions for it. The system is isolated or the system is closed, which means no objects enter or leave the system. Yes, I want you to make a note of this because we're going to make sense out of this diagram here. So this is the system, the one with the boundary here, and the mass is present inside it. Okay. Now, there are two conditions which need to be satisfied. One, the system is closed, and the second, the system is isolated. No external forces act on it. Well, I'm sorry, this. I'm really sorry. This should be the other way around. We don't need this part here. Okay, so the external forces, no external force act on it, and the system is isolated, that is, it is closed. So only when these two overlap, we can say that the system is said to be conserved in momentum. Okay. Now, what is a closed system? Very important. A potential topic for assertion reason type questions. A closed system has no mass entering or leaving, which means the mass is fixed. Again, all of this is in respect to the system represented as a boundary here with two masses in it, M1 and M2. Okay. So when we apply F external is equal to dP by dt, P is mv, so that becomes d by dt of mv is equal to 0, momentum is constant. Now, if mass is changing, this is constant, only this is 0, only when mass is also constant. But if mass is not a constant, then what happens? Because P is equal to mv, by product rule of differentiation, right? By product rule of differentiation, what is d by dt of f of x into g of x? It is f of x into g dash x plus g of x into f dash x, right? So bringing in this to the given equation here, m is f of x, v is g of x. So we have d by dt of p is d by dt of mv is m into dv by dt, f of x into g dash x plus v into dm by dt. Now, if f external is equal to 0, then the second term, v into dm by dt, can still make dp by dt not equal to 0. Why? Because dm is not equal to 0. Why is dm not equal to 0? Because dm is not, sorry, because not dm, because mass is not, because mass is not a constant. And when a function is not a constant, the relative change is not equal to 0. Therefore, the momentum can change. I hope it's good so far, right? So, momentum conservation needs two aspects. One, the system should be the system should be closed, which means there is no object entering or leaving. Why? Because it can influence the dm by dt part of the equation. Now comes the most important part, which is the this is I shouldn't have involved this thing here, which means the f external is equal to 0. F external equal to 0. So the immediate question, what if f external is not equal to 0? What if some external force act on the system? If external force act on the system, then f external is not equal to 0. dp by dt is equal to 0 doesn't hold true, which means the initial momentum will not be equal to the final momentum. Why? Because the external force can change the momentum of the system. Okay? Oh, it's becoming way too much on the theoretical and the conceptual part, isn't it? Okay, my bad. I should have tried to make it a bit shorter, but see, the more I think these elements were really important to understand. That's the reason why I have included all of this in one solution, so that we don't need to repeat it every time in the coming solution wherever we use impulse momentum and conservation of momentum theory. Now, why am I saying all this? Why so much emphasis on F external? Because the next topic that we are going to deal here with the topic of friction. And when friction is taken into account, can we apply conservation of momentum theorem? Is the question. In simple words, is friction internal or external? See, friction can be external if it comes from something outside the system. Well, actually, it can be considered to be external if it comes something outside from the system. It can be considered to be internal if both the objects creating the friction are inside the system. Exactly, as it has flashed in your mind, defining what is your system will in turn influence whether friction is internal or external. To make it more precise, let's take an example here. So we have an object A sliding on a surface S. Object A sliding on a surface S. The surface is not smooth, which means there is friction between the surface and the object A or the block A. Okay. Now, there are two forces acting here. Which are they? Friction due to the contact of A between S acts in two ways. Friction on A due to the surface action, and the reaction friction on the surface due to A. Likewise, friction acting on A due to the surface, friction acting on the surface due to A. Now, you might be wondering, I've repeated the same thing. Yes, but there's a minor difference. What is that? Exactly, the system here is the difference. This system considers, the boundary here considers only A within it. But this system considers both the block and the floor within it. So, in this system, friction acting on A due to source is what? It is an internal force, whereas friction acting on the surface due to A is an external force, but is not acting on A. There's a difference. It is not acting on A. Yes, it is acting on a surface. But if you consider this larger system, Force acting on A is on the system. A force acting on A due to the surface is within the system. Force acting on the surface due to A is also in the system. So there are two internal forces here. There are two internal forces here. That becomes really important. So it is not that this is internal or no, which among these are internal and external. It is important to also it is important to understand which force is acting on which body, because force acting on A, friction acting on A, friction acting on surface, friction acting on A, friction acting on surface. That terminology is important as well. Okay. Now, when the friction is considered in a way that it is acting as an external force outside the system, then final momentum is not equal to initial momentum. If the both objects creating the friction are inside the same system, then final momentum will be equal to the initial momentum. Okay. Okay, now moving further. So we just saw that there are two things. System is closed. I should have made it a bit more accurate while I've used isolated, the phrase isolated and closed. It's really overlapping and the concept might be confusing, right? Okay, my bad. I hope if you follow the lecture so far, it makes sense that whenever I say isolated, I mean closed, and otherwise means F external is equal to 0. Well, it's actually, it would be also correct if you choose the other terminology, but I would choose this rather. Okay. Now, let us see how to define our system. So we have a boy here trying to catch a ball. There are two possible systems. One is the ball alone. Two is the boy alone. Okay. And there is, in fact, even one more where you can just pick both of them together. So, system of choice and the use of impulse momentum or conservation of momentum theorem. You can choose either the ball alone or the ball and the boy, or you can choose ball and the boy on a roll or a ice. Now, this is not related to the question here, but this is related to previous year question and therefore is a potential possibility of future question. So we'll discuss this as well. The system and choosing the theorem. Ball alone, ball and the boy on a roll or an ice. Which among these theorems can be selected, can be chosen to solve physical problems on three different occasions? Conservation of momentum, impulse momentum theorem. Can we use all of them in all the scenarios, or do we have restrictions based on whatever we have discussed so far? So that's what I would request you to think of it, and then maybe discuss among yourself. We have the ball alone. Is f external equal to 0, or is it not? In which case, can we apply conservation of momentum, or should we choose impulse momentum theorem rather? Hope that makes sense, right? So pause the solution here. Take some time. Talk to yourself. Write it down. Maybe you can use since you're writing on paper, you can make use of more space and then just quote here example 1, example 2. Okay, we can't use conservation of momentum in example 1. We can use impulse momentum in example 2. So on and so forth. Or if you're using your iPad or your digital products, what you can do is you can just take it to a PowerPoint, or maybe you can take it to a take it to the custom software you have, notes, and then you can try to draw a diagram and try to make better sense out of it. Okay, but don't just go to the next part of the solution before doing that. Make sure you pause the solution here. You think of what is being asked here. These three different cases. Of course, you can skip this one because we haven't discussed friction so far. But these two, I'm pretty sure you can do that confidently. These two. Okay. Now, external forces present in ball only. When we consider the system as the ball only with the ball, yes, the force is external and therefore momentum conservation cannot be used, which means we use impulse momentum theorem. Now, when we consider ball and the boy, the ground is external and therefore you still cannot use conservation of momentum. I think this is where most of us go wrong. This the second part here. And we are still left with impulse momentum theorem. Now, if the ball and the boy, instead of ground, are considered on a moving skate, then the external force is not present. Of course, given the condition that it is smooth, then we can apply conservation of momentum. Why? Because F external acting here is 0. And therefore, conservation of momentum theorem can be used. This is the crux of the discussion. Yes, I have taken around 20 minutes to explain all this just to make sure that you get a detailed understanding of these three cases here. Okay. So what are the cases? We will discuss these three cases in the next solution. Okay.